Welcome to Norton Chemistry. Today we're going to be doing a topic revision video on electron structure, which is probably one of the more difficult topics in Module 2 of the specification. Make sure you stick around for the exam questions, as application of this content is key to success. Electron configurations. Electrons occupy shells. Each shell can hold 2n² electrons, where n is a principal quantum number. So, for example, the first shell is n equals 1, the second shell is n equals 2, and so on. In the third electron shell, there are 18 electrons because we need to use the formula 2n², where n is 3, and we square 3, multiply by 2, that gives you 18 electrons. Electron shells are made up of orbitals, which are areas of an atom that can hold up to 2 electrons of opposite spin. Remember that definition. Electrons in pairs are both negatively charged, so repel each other, causing them to rotate or spin in opposite directions. So orbitals make up subshells, which make up shells. S orbitals are spherical and p orbitals are dumbbell shaped, so you can see a drawing. And there are 4 orbital types, s, p, d and f. There are 1s, 3p, 5d and 7f orbitals possible per subshell. So in the s subshell there are 2 electrons, and in the p subshell there are 6 electrons, in the d subshell there are 10 electrons, and in the f subshell there are obviously 14 electrons. Within each shell, orbitals of the same energy level are in the same subshells. Subshells have different energy levels. Note that 4s is lower than energy in 3D. So if you have a look at 4s here, it's below 3D over here. So 4s will fill and empty before the 3D orbital. Atomic orbitals with the same energy fill individually first before pairing, and the lowest energy level always fills first. So for example, the 4s is lower energy than the 3D, so the 4s fills first. And then we represent electron configurations using this standard method. So n represents the principal quantum number, x represents the orbital type, so for example s, p, d or f, and y is the number of electrons. So we have the electron configuration of potassium. If we have a look at this periodic table over here, I've color coded the blocks of the periodic table. So to the left we have the s block, then we have the d block in the middle, which is our transition elements, and then the p block to the right, and at the bottom is the f block. So when we're doing our electron configurations, we need to locate the atom on the periodic table and identify which block it's in, and then we can identify where the highest energy electrons are going to be located. So for example, for potassium, we can see in the periodic table it's in the red s block. So in the electron configuration, we can see that the electrons furthest to the right are in the s subshell, and then we can also see that it's 1, 2, 3, 4 periods down the periodic table. So it's the 4s subshell where the outer electrons are located. And then you can also do the electron configuration of ions. So for the K+ ion, you're obviously losing an electron from potassium. So the electron configuration is going to be the same electron configuration as argon, which we can see over here in the P block. So the new highest energy electrons are going to be located in the P block. Then there's the anomalies, which are chromium and copper. So they have anomalous electron configurations. So if we have a look at the electron configuration of chromium, we can see that we have 1 electron in the 4s subshell, and then we have the 3d subshell filling with an extra electron. So normally you would expect it to be 4s2, 3d4, but it's actually 4s1, 3d5. It's just one of those things that you have to learn. And then the same goes for copper, so it's got only 1 electron, a partially filled 4s subshell, and then an extra electron. So normally it would be 4s2, 3d9, but instead it's 4s1, 3d10. Again, one of those things you just have to learn, and they will test you on it. Don't expect them to not test you on it in exam questions. So we've got some exam questions. Electrons occupy orbitals which are arranged in energy levels. In the diagram below, each box represents an orbital and each electron is shown as an arrow. Label the subshells and add arrows to show how electrons occupy orbitals in an atom of oxygen. So this is the electrons in a box model, and each arrow represents 1 electron. Each box represents 1 orbital, so we can see that this 1s orbital has 2 electrons in it because that's the maximum number of electrons that an orbital can hold. And the arrows are drawn in opposite directions to show that the electrons are spinning in opposite directions, as we mentioned earlier. So if we have the 1s orbital here, if we have a look at our periodic table over here, we can see that we have the 1s orbital first, Then we have the 2s orbital. So this orbital here is going to be the 2s, and that's going to be fully filled as well because oxygen has its outer electrons in the 2p subshell. So this is the 2p subshell here, and if we have a look at oxygen, it has 1, 2, 3, 4 electrons in the p subshell. So we need to singly fill the orbitals first, remembering from earlier that orbitals fill singly, then they pair up. Only this orbital to the left is going to have a complete pair of electrons. These two orbitals will remain singly filled. Question 2. Selenium is in the same group of the periodic table as sulfur. Complete the full electron configuration of a selenium atom. So let's identify selenium. We know it's in the same group as sulfur. So if we have find sulfur first, then we can find selenium. Selenium we can see is located below sulfur, and it's in the 4th period of the periodic table, and it's in the p block. So its outer electrons are going to be in the 4p subshell. They've already given us 1s2, so we can go on from there. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, and then if we have a look again, we can see that it has 4 electrons in the 4p subshell, so it's going to be 4p4. And notice it's a selenium atom, not a selenium ion. Question 5. The electrons in the second shell of a nitrogen atom are found in an s orbital and 3 p orbitals. State, in words, the 3D shape of an s orbital and a p orbital. So s orbitals we know from earlier are spherical, and p orbitals are dumbbell shaped. Different examples have different names for the shapes of p orbitals, but for OCR it is dumbbell shaped. Describe the relative energies of the 2s orbital and each of the 3 2p orbitals in a nitrogen atom. So the p orbitals have a higher energy than the s because the p orbitals are further from the nucleus, and the s orbital fills before the p orbital. And then the p orbitals all have the same energy. It's random which orbital in the 2p subshell will fill first. Thanks for watching. Be sure to check out my website. I've got lots of resources available, including my A-level chemistry notes and flashcards. You can also book a tutoring session. Send me a message and I'll book you in as soon as possible. Make sure to check out my redox revision video. It's in the top right hand corner now.